Okay, so good morning to all of you. In this class, I am going to explain the maximal assignment problem. Okay. So as I have discussed in the previous classes, the assignment problem is by default minimization problem. So transportation problem and assignment problem both are by default minimization problems. Okay. So in some cases, the entries represent profits, returns, etc. So in that case, the problem become a maximal assignment problem or maximal transportation problem. Okay. So how do we convert maximal assignment problem to minimization problem? Suppose already we have discussed in the linear programming problem. So the conversion of minimization problem to maximization problem by using the relation minimum z equal to minus max minus z. Okay. So in that relation, if you replace z by minus z, we get minimum minus z equal minus maximum of minus z, that is max z. So from that relation, max z equal to minus minimum minus z. Okay. So to convert maximal assignment problem or maximal transportation problem, we have to consider the negative entries of the given entire matrix. That means we consider the negative sign for the cost coefficients in the objective function. Okay. So maximal assignment problem. So assignment problem may have an objective function of maximizing the profit. Okay. So you have to observe this point. So what is the nature of the objective function? Suppose if you asked to solve the following assignment problem, so by default it is a minimization problem. Suppose in some cases the meaning of the entries in the given matrix given particularly. Okay, so in that case we have to observe whether the entries are profits or returns, etc. So in that case, that means the given problem is maximal assignment problem. Okay. So in this case, we convert into minimization problem by subtracting the entire matrix from its largest element. Okay. So what is the meaning of this subtracting entire matrix from its largest element? Okay, entire matrix from its largest element. Okay. So by using the relation, so minimum ZD max ZD called, this is the relation. So max ZD called minus minimum of minus Z. So max Z called minus minimum of minus Z. This is the relation to convert maximization problem to minimization or minimization to maximization. Okay. So here we have given a maximization problem. So to convert that maximization problem to minimization problem, we have to consider minimum of minus Z. So we have to consider negative of the objective function and we minimize that function. So we have to take negative of the objective function means we have to take negative sign for each entry in the matrix. Okay. So what is the Hungarian method? The Hungarian method assumes that each entry in the matrix should be non-negative. So here we have negative entries. So for that we have to add sufficient positive quantity to each entry. Okay. So suppose the largest entry in the matrix is, suppose for example 10. If we add 10 to each entry, then each entry become greater than or equal to 0. So adding largest element to the entries of this matrix containing negative signs of each entry. Okay. So that means in other words, subtract each entry from the largest element of the matrix. Okay. So that is the way to convert maximal assignment problem or maximal transportation problem to minimization problem. Okay. So subtract entire matrix from its largest element. Then the maximal assignment problem converts to minimal assignment problem. So this will be given in one more question. How do you convert maximal assignment problem to minimal assignment problem? Okay, so by subtracting the entire matrix from its largest element, the maximal assignment problem can be converted to the minimal assignment problem. Okay, right. So consider this problem. A company has 5 jobs to be done. The following matrix shows returns in rupees. On assigning mission I to job J, find the optimal assignment which gives maximum returns. So write this table. So there are 5 missions, 1, 2, 3, 4, 5. There are 5 jobs, A, B, C, D, E. So these entries represent returns. Returns means profits in rupees corresponding to missions and jobs. So we have to find the optimal assignment which gives maximum returns. So here the nature of the entries in the matrix are returns or profits. Okay. So in general, returns, profits are to be maximized. Okay. So by observing this problem, the given assignment problem is maximal assignment problem. Okay. Write the solution. First, verify whether it is balanced or unbalanced. The number of rows is 5. Number of rows 5, number of columns also 5. So 5 rows, 5 columns. So problem is balanced. Next. So we have to convert this maximal assignment problem to minimal assignment problem. For that, we take negative of the objective function. That means we take a negative to each entry. This is -5, -11, -10, etc. So you have to take minus sign for each entry. So that is minimum of -j. So to solve this problem using Hungarian method, what is the assumption? Each entry should be non-negative. Suppose there is a negative entry, we have to convert it into positive entry by adding some sufficient positive value. Okay. So in the entire matrix, what is the largest element? In the entire matrix, largest element is 14. Okay. So after taking negative sign for each entry, we have to add 14 to each entry. That is the largest element 14 to each entry. So that is the meaning. In other words, adding 14 to each negative entry means we have to subtract each entry from its largest element, that is 14. Okay. So convert the maximization problem to minimization problem. Convert the maximization problem to minimization problem. How do you convert? Subtract all elements of the matrix. Subtract all elements of the matrix from its largest value 14. Subtract all elements of the matrix from its largest value 14. Okay, so largest value in the entire matrix is 14. We have to subtract each element or each entry from 14. Okay, right. Subtract 5 from 14. So 14 minus 5, 9. Next 14 minus 11, 3. 14 minus 10, 4. 14 minus 12, 2. 14 minus 4, 10. So like that, fill the other places. 14 minus 2, 12. 14 minus 4, 4, 10. 14 minus 6, 8. 14 minus 3, 11. 14 minus 5, 9. 14 minus 3, 11. 14 minus 12, 2. 14 minus 5, 9. 14 minus 14, 0. 14 minus 6, 8. 14 minus 6, 8. 14 minus 14, 0. 14 minus 4, 10. 14 minus 11, 3. 14 minus 7, 7. Again 14 minus 7, 7. 14 minus 9, 5. 14 minus 8, 6. 14 minus 12, 2. 14 minus 5, 9. Okay, so subtract all elements from the largest value 14. So this is the way to convert maximal assignment problem to minimization problem. This will be given in 1 mark questions. How do you convert maximal assignment problem to minimization problem? Okay. So this is our cost matrix. Okay. Now this is our cost matrix which represent minimization problem. So use Hungarian method to solve this problem. So first step, what is the first step? We find row minimas. Right here, row minimas. First row minima 2. First row minima 2. Second row minima 8. Third row minima 0. Fourth row minima 0. Fifth row minima 2. So right here row minima values. So in first step we find possible assignments for rows. For that we identify row minima and subtract that row minima from the entries of that row. So we get possible assignments for rows. Okay, right. And the next step, obtain the next table or matrix by subtracting the minimum of each row from the entries of that row. Obtain the next table or next matrix by subtracting the minimum of each row from the entries of that row. Okay, so this is first matrix, right? Subtract 2 from first row. Subtract 2 from first row. First element 9, 9 minus 2, 7 here. Next to 3 minus 2, 1. 4 minus 2, 2. 2 minus 2, 0. 10 minus 2, 8. Next to subtract 8 from second row. 12 minus 8, 4. 10 minus 8, 2. 8 minus 8, 0. 11 minus 8, 3. 9 minus 8, 1. From third row and fourth row, subtract 0. So they remain same. Third row and fourth row remain same since we have to subtract 0. Next, subtract 2 from last row. So 7 minus 2, 5. 5 minus 2, 3. 6 minus 2, 4. 2 minus 2, 0. 9 minus 2, 7. Okay. So at present, we got possible assignments for rows. Okay. Next, similarly, we find possible assignments for columns. For that, we find column minimas here. So here, first column minima is 4. So right here, column minimas. First column minima is 4. Second column minima 0. And third column minima 0. Fourth column minima 0. And fifth column minima 1. So these are column minimas. So now subtract these column minimas from the entries of that column. Okay. Right step. Obtain the next matrix or table by subtracting the minimum of each column from the entries of that column.
హలో సార్.
Ah,
లిమిట్ రీచ్ అయిపోవడం వల్ల మిగతా వాళ్ళు జాయిన్ అవ్వలేకపోతున్నారండి సార్.
limit ఏంటి?
కొన్ని గూగుల్ మీట్ లింక్స్లో మాక్సిమం 100 మెంబర్స్ అలా ఉంది సార్ లిమిట్. మా ఫ్రెండ్స్ ఎవరు జాయిన్ అవ్వలేకపోతున్నారంట.
మనకి ఫస్ట్
లిమిట్
నుంచి
రీచ్
ఉంది. మనకి ఫస్ట్ నుంచి ఉంది కదా.
ఏమో సార్, ఇక 4-5 మెంబర్స్ లిమిట్ కెనాట్ జాయిన్, లిమిట్ ఎక్సీడెడ్ అని వస్తున్నాను సార్.
1 minute.
నిన్న కూడా అలాగే ప్రాబ్లం వచ్చింది ఇంగ్లీష్. ఓకే సార్.
నాట్ 1 అన్నారు కదా. మనకి ఆ ప్రాబ్లం లేదమ్మా. ఇది హలో, రెస్పాండ్ అవ్వండి. హలో,
ఓకే సార్. ఓకే సార్, ఒకసారి
అది
అడుగుతాను సార్.
కాలేజీ మెయిల్ ద్వారా దీన్ని రిజిస్టర్ చేసాం, అందువల్ల అది 250 దాకా ఉంది. హలో,
ఓకే
మనకి
సార్.
ఇప్పుడు దాకా ప్రాబ్లం రాలేదు కదా.
అవును సార్, అవును సార్.
అది ఇంగ్లీష్ వాళ్ళకి అది
మెనీ ఆర్ ఫేసింగ్ ప్రాబ్లం.
కాలేజీ మెయిల్ ద్వారా వెళ్ళుంటారు. అది ఒకసారి కన్ఫర్మ్ చేసుకోండి. అవుతారు, ఇబ్బంది లేదు.
ఓకే సార్.
Right, obtain the next table by subtracting the minimum of each column from the entries of that column. Okay, the first column minimum 4, subtract 4 from first column. 7 minus 4 3, 4 minus 4 0, 11 minus 4 7, 8 minus 4 4, 5 minus 4 1. And second, third and fourth columns minimum 0. By subtracting 0, those 3 columns remain same. Second column remains same, third column remains same, fourth column minimum, fourth column remains same, since we subtract 0. Next, subtract 1 from last column. So 8 minus 1 7, 1 minus 1 0, 8 minus 1 7, 7 minus 1 6, 7 minus 1 6. Okay, right. So at present we have at least one possible assignment for rows as well as for columns. Now we have to fix the assignments. For that, we draw minimum number of lines to cover all the zeros. So draw minimum number of lines to cover all the zeros. Right. For that, first consider first row. Observe first row. How many number of zeros? In first row, only 1 0. So first row contains only 1 0. That is, row 1 contains only 1 0. So row 1 contains only 1 0. So circle that 0 and fix column. So draw vertical line. Circle that 0 and fix column. That means draw vertical line. Okay. Next, come to second row. Second row contains more than 3 zeros. Skip the second row. Next, third row contain no zero. Since already this entry is fixed, so you need not consider fourth column, since already fourth column is fixed. So in the remaining entries there is no zero in third column. Okay, skip the third column. Next, fourth column contain only 1 0. Sorry, row 4 contains only 1 0. So row 4 contains only 1 0. Circle that 0 and fix the column, that is second column. So cross off second column. Next, fifth row contain no zero. So you have to consider only these 3 entries. Okay. So fifth row contains no zeros. Skip the fifth row. Okay, right. Now observe, still there are zeros not covered by lines. Still there are zeros not covered by lines. Then go for columns. So go for first column. Observe first column. First column contain only 1 0. So column 1 contains only 1 0. Circle that 0 and fix corresponding row, that is cross off row 2. So cross off row 2. Okay, right? Second column already fixed, third column no 0, fourth column already fixed, fifth column no 0. Okay, so observe all zeros are covered by lines. So there are no zeros not covered by lines. So all zeros are covered by lines. Okay, so then verify the optimality condition. How many assignments we have made? Only 3 assignments. That means we have drawn only 3 lines, 1 horizontal line and 2 vertical lines. So number of lines drawn not equal number of rows. So number of lines drawn 3, number of rows drawn 3, number of lines drawn 3, number of rows 5. Okay, both are not equal. Number of lines drawn not equal number of rows. So present assignment is not completed. That is, assignment is not completed. So I have to improve the assignment. How do you improve the assignment? For that, we find possible assignments. How do you find possible assignments? Among uncovered entries, identify the least value. Among uncovered entries, identify the least value. What is the least value of uncovered entries? 1. Okay. Among uncovered entries, least value 1. Okay. So minimum of uncovered entries is 1. This is minimum of uncovered entries. Right. So add 1 to the entries in the intersection of covered rows and columns. Add 1 to the entries in the intersection of covered rows and columns. Next, subtract 1 from uncovered entries. Subtract 1 from uncovered entries. The remaining entries remain same. Okay, right? So this is uncovered entry. So here subtract 1. So 3 minus 1, 2, 1. This remains same since it lie in covered column only. So this remains same. Again 2 uncovered entry, subtract 1, 2 minus 1, 1, 0. It remain in covered column only. So it remains same. 7 uncovered entry, subtract 1, 7 minus 1, 6. Next, this remains same, 0. So this is in the intersection of covered row and column. So we have to add 1. So 2 plus 1, 3. This remains same, 0. Again, this is intersection of covered row and column. We have to add 1 here, 3 plus 1, 4. And this remains same, 0. Next, this is uncovered entry, subtract 7 minus 1, 6. This remains same, 2, 9 minus 1, 8. This remains same, 0. 7 minus 1, 6. Okay. Similarly, 4 minus 1, 3. This remains 0. This remains same. 10 minus 1, 9. 3 remains same. This remains same. Next, this is uncovered entry. 6 minus 1, 5. Next, 1 minus 1, 0. So this is new possible assignment. This is new possible assignment. 3 remains same. Next, subtract here. 4 minus 1, 3. This 0 remains same. 6 minus 1, 5. So the new matrix, the new possible assignment is this one. This is the new possible assignment. Okay. So there are new possible assignments in this matrix. Again, repeat the same process. We have to fix the assignments. So draw minimum number of lines to cover all the zeros. Right. So observe first row. So observe first row. First row involve only 1 0. That is, row 1 contains only 1 0. So circle that 0. Circle that 0 and fix column. So cross off column 4. Next, row 2 contain more than 1 0. Skip row 2. Row 3 no 0. Row 4 only 1 0. So row 4 contains only 1 0. circle that 0 and fix the column, fix the second column. So cross off second column. Next, fifth row contain only 1 0. Row 5 contains only 1 0. Circle that 0 and fix column, that is fix column 1. So cross off column 1. So all rows are verified. So observe, still there are zeros not covered by lines. So then go for columns. Already first two columns are fixed. You need not check the first two columns. So third column. So third column contain only 1 0. So column 3 contains only 1 0. Circle that 0. Since it is in the column, we have to fix row. So cross off second row. Cross off second row. Next, fourth column fixed. Fifth column, no 0. So now observe, all zeros are covered by lines. So there is no 0 entry in uncovered entries. So all zeros are covered by lines. Right, now verify the optimality condition. So number of lines drawn, 1 horizontal line and 3 vertical lines. The number of lines drawn not equal number of rows. Number of lines drawn 4, number of rows 5. So still the assignment is not completed. Still the assignment is not completed. So we have to improve the assignment. How to improve the assignment? Again, identify the smallest value in the uncovered entries. So what is smallest value in the uncovered entries? 1. Okay. So minimum of uncovered entries C equal to 1. As usual steps, add 1 to the entries in the intersection of covered rows and columns and subtract 1 from uncovered entries as usual. Okay, right. So first, these two entries remain same since they lie in covered column only. So 2, 1. And this is uncovered entry, subtract 1. 1 minus 1, 0. So this is new possible assignment. This is new possible assignment. Next, this remains same. This 0 remains same since it lie in covered column only. Next, this is uncovered entry, subtract 1 here, 6 minus 1, 5. Next, this is in the intersection of covered row and column. We have to 1 here. So 0 plus 1, 1. So here observe, the previous possible assignment is removed here. The previous possible assignment is removed here. Okay. Next, 3. It is also in the intersection of covered row and column. We have to add. So 3 plus 1, 4. Next, this is 0. It remains same. And this is in the intersection of covered row and column. We have to add 4 plus 1, 5. And this 0 remains same since it lie in covered row only. Okay. Next, these two entries remain same. 6, 2. Here subtract 8 minus 1, 7. This remains same, 0. 6 minus 1, 5. Next, these two also remain same, 3, 0. Here subtract 1, 9 minus 1, 8. These 3 remain same. And here subtract 5 minus 1, 4. Next, these two entries remain same, 0, 3. And here subtract 3 minus 1, 2. This remains same, 0. Here subtract 5 minus 1, 4. Okay, right. So this is the new matrix in which we have new possible assignments. Again, we have to fix the assignments. So draw minimum number of lines to cover all zeros. Right, observe first row. So first row contain 2 zeros. Keep first row. Next, second row contain 2 zeros. Skip second row. Third row contain only 1 zero. The third row there is only 1 zero. So row 3 contains only 1 zero. Circle that 0 and fix column, that is cross off column 4. Next, fourth row contain only 1 zero, that is row 4 contains only 1 zero. Circle that 0 and fix the column, that is cross off column 2. Next, row 5 contain only 1 zero. Row 5 contains only 1 zero. Circle that 0 and fix column, that is cross off column 1. So all rows are verified. Still there are zeros not covered by lines. This is 0 not covered by line. This is 0 not covered by line. This is 0 not covered by line. So go for columns. First 2 columns are fixed. You need not check the first 2 columns. Third column. So third column contain more than 1 zero. The third column contain 2 zeros. So skip the third column. Already fourth column fixed. You need not check. Next, fifth column. So fifth column contain only 1 zero. This is column 5 contains only 1 zero. This is column 5 contains only 1 zero. So circle that 0. Since we are verifying columns, we have to fix row. So cross off second row. Cross off second row. Okay, so columns are verified. Now observe the uncovered entries. Still there is a 0 not covered by line. This is 0 not covered by line. This is the 0 not covered by line. So go for rows. Repeat the same process. First row. So in first row we have only 2 entries. In first row we have only 2 entries, 0 and 5. So row 1 contains only 1 zero. So row 1 contains only 1 zero. So circle that 0 and fix column. Cross off column 3. Okay, now in uncovered entries there is no 0. Okay, so now all zeros are covered by lines. Now all zeros are covered by lines. So observe how many number of lines we have drawn. 1 horizontal line and 4 vertical lines. And there are 5 circled 0 entries. Okay, so number of lines drawn equal number of rows. Number of lines drawn equal number of rows. So assignment is completed. Assignment is completed. So present assignment is an optimal assignment. Number of lines drawn equal number of rows. So assignment is completed. Okay. So consider this is a original matrix. This is original matrix, right? So optimal assignment is okay. So first two. Here missions are 1, 2, 3, 4. Jobs are A, B, C, D, E. First take missions 1 to 5. Take missions 1 to 5. Okay, right. So the circled 0 entries represent fixed assignments. Okay, so that is first one is 1, 3. That means 1 is assigned to C. So mission 1 is assigned to job C. Here 1 to C. Mission 1 is assigned to C. Next, this entry is 2, 5. That is mission 2 is assigned to job E. So mission 2 is assigned to job E. Next, third row and fourth column. This is, that means third row and fourth column. This is. So mission 3 is assigned to job D. Mission 3 is assigned to job D. Next, fourth row, second column. This is fourth row, second column. That is mission 4 is assigned to job B. Mission 4 is assigned to job B. Next, fifth row, first column. Okay, so fifth row, first column. That is mission 5 is assigned to job A. Mission 5 is assigned to job A. So this is the optimal assignment. So here observe, there should be no repetition here. So A, B, C, D, E. So there should be no repetition here. Okay, since it is one-to-one correspondence, one mission is assigned to only one job, or one job is assigned to only one mission. So this is one-to-one correspondence. So this is the optimal assignment for this problem. Now what is maximum returns? What is maximum return? So what is maximum return means profit. Okay, so from the original matrix we have to consider the corresponding entries. From original matrix we have to consider the corresponding entries. First assignment is 1 to C, that is 1 to C, that is this is 10. The corresponding return is 10. If mission 1 is assigned to job C, the corresponding return is 10 rupees. Next, 2 to E. 2 to E, this is 5. Next, 3 to D. So 3 to D, 14. Next, 4 to B. So 4 to B, this is 14. Next, 5 to A. So 5 to A, 7. So the maximum returns is sum of all these 5 entries. So 10 plus 5 plus 14 plus 14 plus 7. This is 50 rupees. Okay, so the maximum returns is 50 rupees. So this is optimal assignment. So this is the way to solve the maximal assignment problem. Okay, so by default the assignment problem is minimization problem, but in some cases the nature of the entries of the matrix is returns or profits, etc. So in such case the problem is maximization problem. So you have to convert it into minimization problem. For that we have to consider negatives of each entry. But to apply Hungarian method, the assumption in the Hungarian method is each entry should be non-negative. So we have to make all entries as positive by adding some sufficient positive value. Okay, so in other words, since each entry is negative, we are adding positive. That means in other words, we have to subtract each entry from the largest value of the matrix. Okay, so that is the way to convert a maximal assignment problem to a minimal assignment problem.